Okay, we're going to cover standard T2 today, which involves solving right triangle story problems and using inverse trig functions to solve the angle. And then the type 4 will be that you can solve a right triangle problem that has two missing variables. Okay, so first thing that we have to do is talk about what this means, since we haven't talked about inverse trig functions. So far we've learned to evaluate trig functions for specific angle measures. So I've said, okay, find the sine of 30, and then you find the value of that. Now we're going to do the backwards part of that, which is using the values to find the angles. In Algebra 2, we spent many chapters looking at inverse functions, and we've actually already talked about some of this. What were some of the examples? Well, we had square root paired with quadratic. Those are inverse functions. Along with that, cube root paired with cubic functions. We have logarithmic, which is the inverse of exponentials. And let's talk about absolute value. We've talked about quadratics, cubics. Why am I drawing a blank? Logs, inequalities. Oh, we'll just list those ones because we have linears and we have some others. But these are the three main groups of inverse functions. Some of the characteristics of the inverse functions. Their main characteristic is they undo each other. So they cancel each other out. When you take the square root of a square, you cancel out the function part of it. Their x and y's are flipped. So domain and range are flip-flopped. So the x's in one are the y values in the other, and vice versa. And one of the last characteristics is that their graphs are reflections of each other over the line y equals x. When we go to find the opposite function of sine and cosine, we run into a problem. And the problem we run into, because we've already seen like sine looks like this, well, if we were to flip the graph over the line y equals x, it would end up looking like this. And that's a problem because no longer is it a function. It doesn't pass the vertical line test. I think in here I want you to put they don't pass the VLT. Therefore, or however, what happens with trig functions is they only use a chunk. And they use a chunk where if they were to flip that chunk of the graph, it would pass the vertical line test. We're not going to get into the specifics of it. I might have you draw a couple graphs. Sorry. Yeah. Of course. Sorry. Thanks for your patience. I should have grabbed this stuff before. Oh boy. Oh dear. Oh dear. Oh, here we go. Whew. Right. Alright, so explanation of an inverse trig function and its graph. Okay, first thing is that when you find the value of a trig function on the calculator, it only finds the value in what we call the principal branch. And again, the principal branch of the graph is the part of the graph where you can flip it to represent the opposite or inverse function, and it would pass the VLT. And that's why when you do your hand trick, or when you find a value on the calculator, knowing what quadrant the angle is in is important, because it's not going to find you the correct value. It's not going to make it positive or negative, because it only gives you the angle in the principal branch calculator. Okay. So inverse trig functions only utilize the chunk of the graph that, when flipped over y equals x, will still pass the vertical line test. In order to have an inverse trig function, in order to be a function, it has to pass the VLT. Okay. The notation, so like up here, square root and quadratic. Quadratics, you know it's a quadratic if something's being squared. You know it's a square root function if you have the root symbol there. To know if you're dealing with an inverse trig function, or the opposite function of sine, cosine, tangent, the one that will undo it, notation for inverse trig functions is labeled like this. So when you see a -1 power on sine, that represents, that's the inverse trig function that would cancel out the sine function. They're using the idea like if you had sine, and then if you flipped it, it'd be 1 over sine. They'd cancel each other out. That's not really what's going on here, but that's why they use the notation of -1 to represent the opposite or inverse trig function for sine. So the notation for inverse trig functions is having a -1, or this is another way to say the same thing. If they put the word arc in front of the function, that word arc identifies an inverse trig function. Okay. Note, sine to the -1 of x is the inverse function. Sine of x raised to the 1/2, or sorry, to the -1, means it's the reciprocal. Okay, so where that -1 is located is essential. If it's attached to the sine, it's the inverse function. If it's on the outside with parentheses, then it's the reciprocal, and then that would become 1 over sine, not the inverse function. Okay, now we're going to practice with some of this, because like we'll see inverse trig functions. Again, I'm just trying to teach you the basics for this stuff. We'll dig into some other nitty-gritty stuff in trig after we do the calculus, but I at least need to give you enough where you can solve right triangle word problems. Alright, so suppose you have the job of measuring the height of the local water tower. Climbing makes you dizzy, so you decide to do the whole job at ground level. You find that at a point 47.3 meters from the base of the tower, you must look up at an angle of 53 degrees to see the top. How high is the tower? So first thing I'm going to do is draw a scenario, which is going to end up looking like a right triangle. 47.3 here I am. Okay. 47.3 is how far I'm standing from the base of the tower. And here's the tower. I don't know the height. That's what I'm trying to find. So I'm going to make that a y value because it's vertical. I know that the angle of elevation, or how I have to raise my eyes to see the top of the tower, that's going to be 53 degrees. As long as you have one angle and one side of a triangle, you can solve for the missing variable. And what you're going to use here is a trig function. And you have, I'm going to write SOHCAHTOA here, you have three options, or three main options. You have sine, cosine, or tangent. You need to pick the function that relates this angle, the opposite side to that angle, and the adjacent side. The function that does that is tangent. So we're going to write tangent of theta, which my theta is 53 degrees, is equal to the ratio opposite over adjacent. And then if I have to solve for y, I'm going to multiply both sides by 47.3. And then get y equals 47.3 times tangent of 53 degrees. And then I'm going to punch that out on my calculator. Now, make sure that your mode is in degrees, otherwise it's going to screw up your answer. And I'm going to go ahead and take 47.3 and multiply it by tangent of 53. And I get 62.76. Now, I haven't said this yet, but make sure you always go to 3 decimal places. That's what they require in the AP exam, and so we're just going to get, into a good habit of it. And we're looking at meters. Now, this is not taking into account the height of me. So the height of me is I'm about a meter and I think 1.7 meters. So we're going to add 1.7 meters. And so your final tower height would be 64.469 meters. Okay. Example 2. A ship is passing through the straits. At its closest point of approach, the radar determines that the ship is 2,400 meters away. Later, the radar determines that the ship is 2,650 feet away. Now, I'm going to draw a little point here. Okay, so it's passing through. Here's my little ship. Okay. At its closest point of approach, well, the closest point between two spots is a straight line. So at this closest point, it's 2,400 meters away. This is the straight. Okay. This is the ship. It travels a bit. Then they take another radar, look at it. They're saying, okay, at this point over here, you're 2,650 feet away. That's my length between both spots. I have a right triangle. We're supposed to find by what angle do the ship's bearing from the strait change. So I'm looking for this theta here, or how did that angle have to move in order to get those two distances as the ship is traveling. Alright, so as long as we have two values and theta, we go back up to here, SOHCAHTOA, and I'm looking for either sine, cosine, or tangent, the one that associates this angle that I'm looking for, the adjacent side, and the hypotenuse. The one that does that is cosine. So I'm going to set up my problem as cosine of my angle, so cosine of theta, is the adjacent over hypotenuse. Okay. Now, when you're trying to find theta, theta right now is stuck in the argument of cosine. Argument is just, it's cosine of something. So the argument is what's in parentheses. We need to get rid of this cosine somehow. The only way to cancel out a function, like the only way you can cancel out a log, is to use its inverse. We're going to use the inverse for cosine. So the inverse for cosine is cosine to the negative 1. We're going to do it to both sides. And so we get cancel theta. Now over here, cosine to the negative 1 of 2,400 over 2,650. I'm going to do that on my calculator. Again, make sure you're in degree mode. The inverse cosine is if you hit second, and then it's in little blue here, so cosine to the -1, then you put in that fraction, and voila, you get theta equals 25.088 degrees. Okay, so that's my answer for A. For B, how far did the ship travel between the two observations? Well, we can do this one of two ways. I'm looking now for this value here. I can use the Pythagorean theorem because I have both sides. But since we're practicing with inverse trig functions, I'm going to use the inverse trig function here, or at least a trig function. So now that I know what this angle is, I'm going to use the trig function that associates this angle, the opposite side, and the hypotenuse. So I'm going to use sine. So sine of 25.088 degrees is equal to the opposite over hypotenuse. Okay, so I'm going to multiply both sides by that value. And then punch it out. Now, notice there's a whole lot of decimals here. I want you to get used to storing something that looks like that if you're going to use it in another problem. There's something called round-off error that if you're not careful with, the more you use the number, if you've rounded, it's going to make your other answers off by a lot. So we're going to store it. To store, you're going to hit the store button at the bottom. Then we're going to store it as x. That means whenever I put x in my screen here, it's going to use that decimal as its value. So then we have 2,650 sine of x. So automatically it's going to plug that in for x and give me the correct length. And we are looking at miles. There you go. Or meters, maybe. Yeah. Okay. Last problem. Traveling across flat land, you notice the mountain directly in front of you. Its angle and elevation to the peak is 3.5 degrees. After you drive 13 miles closer to the mountain, the angle of elevation is 9 degrees. Approximate the height of the mountain. Okay, we got to draw a picture. Mountain, height, here. You're in a little car and you're traveling towards it. Let's say you take your first reading. Here's my car. Okay, you take your first reading here. Angle of elevation to the top of the peak is 3.5 degrees. You drive 13 miles closer and then you take another reading. And now you're at 9 degrees. And this is 13. We're supposed to approximate the height of the mountain. So I'm looking for that value there. Okay. We have a problem here because really in either case, like if we use the big triangle, you have 13 and then you have this missing length. So I don't have that full length. So you have a variable here. We're going to put that variable as x. And if you use the smaller triangle, you only have one piece of information. When you have two variables or two different things that are missing in the problem, you need to use systems of equations here, or two equations that represent this scenario. And since you have two different triangles, we're going to use that as my two equations. So, step 1, writing your two equations. We have two angles. We need a trig function that relates the angle and the sum of the sides that we have. In both cases, we don't have the hypotenuse, so we're going to use tangent because tangent relates an opposite side to the adjacent side. So our first one is going to be tangent of 3.5 degrees is equal to the opposite side over the adjacent. Now the adjacent here is 13 and this variable, so we're going to write 13 plus x. Then, the next triangle here, we have tangent of 9 degrees. That's going to be equal to just y over x, so opposite over adjacent. Okay, so two equations that represent the same scenario. Tangent of 3.5 and tangent of 9. I can find those values. Tangent of 3.5 is that decimal. I'm going to go ahead and store that as x. And so tangent of 9 is that decimal. I'm going to go ahead and store that as A. Okay. So tangent of 9 is A. Tangent of 3.5 is X. Okay. So I know whenever I have to plug that out, I'm going to use those variables, just so that everything's as accurate as possible. All right, systems of equations means in both cases we want to get one of the variables by themselves so we can set them equal to each other. I'm going to go ahead, and since y is by itself on the top and the bottom here, I'm going to go ahead and multiply this equation by 13 plus x on each side. So y is going to equal tan of 35 times 13 plus x, and then I'm going to multiply both sides here by x, so y is going to equal tan of 9 times x. Okay. And then I'm going to take tan of 9, and since that's equal to y, I'm going to plug it in for y in my next step. And I'm going to go ahead and distribute those through. And now I'm going to solve for x. Okay. So this is where it gets a little bit tricky. I'm going to subtract tan of 35x. So you have tan 9x minus tan of 35 degrees x equals tan of 35 degrees times 13. Now I know all of these are decimals, but to be as accurate as possible, I'm trying to keep it so I can use my stored values eventually. Now I'm going to factor out an x. Now you could punch this out, but I'm going to factor out an x. We're almost done. Then I'm going to divide both sides by this expression to get x by itself. And then what that does is it gives me this messy looking fraction, but it's a messy looking fraction I can put into my calculator. So I'm going to take 13, tangent of 3.5, which I've been writing 35, sorry. Tangent of 3.5 was x. So on the top I'm going to have x. Maybe I'll put the parentheses around that. Then we're going to divide that by tan of 9, which was a. That's what I stored it in. We're going to subtract tan of 3.5, which I had stored as x. Hit enter, and I'm getting 8.18. Okay, now 8.18 is this value here, not the height of my mountain. So there's two things you can do here. You can take, oops, I should have made that 1.78. You can take this value and go back up to one of these problems here and plug it in, which is what I'm going to do. So, fourth step. I'm going to take this value and I'm going to multiply it by what I got for my x. And I'm not going to store this one because if you just do like times, it'll automatically use that whole decimal. So times tan of 9, which was a, and I get 1.295. Now that seems really small for a mountain, but we're talking about miles. That's our unit. So 1.295 miles is a pretty typical answer. Okay, and I think that's, yep. We'll obviously have more practice on this. This is the most, this is the proficiency type problems, and then this one we just did with two variables, that's the 4 type problem.